Today we're going to be practicing using a line to describe a relationship. And so in this example, Kendra likes to watch crime scene investigation shows on television. She watched a show where investigators use a shoe print to help identify a suspect in the case. She questioned how possible it is to predict someone's height from his shoe print. To investigate, she collected data on shoe lengths in inches and height in inches from 10 adult men. Her data appear in the table and scatter plot below. So, is there a relationship between shoe length and height? Well, in the table, we can see that we have a variety of shoe lengths and we have their heights. And notice how in our table, they're not organized from smallest to largest. So we're going to look at the scatter plot. And so all of our data is arranged here. And we can see as the shoe length increased, the height of the person increased. So since that's moving in tandem, we could say that it's a positive relationship. Where the shoe length increases, so does the height. So our next question says, how would you describe the relationship? And then well, we said, as shoe length increases, so does the height. So it would be a positive correlation. And then do the men with longer shoe lengths tend to be taller? And so as we look at the shoe lengths, as those increased, the heights also increased. So that is a true statement. And then the last question is it a strong or weak relationship? So for this, we're going to see if we can tell if the data is aligned, is it clustered together, what kind of, based on the correlation, the strength or weakness can it be? So we can see that it's somewhat clustered together. We can tell where the trend line would fall approximately. So it looks like it's a fairly stronger relationship than weak. We just don't know how strong it is. But we do see how it is getting aligned somewhat. So we'd say more strong than weak. So typically at this point, we want to try to come up with an equation to represent our data. So here at the right, there's a scatter plot of the data with two linear models. One model is y equals 130 minus 5x, and that's denoted by the black line here. And the other model is denoted by y equals 25.3 plus 3.66x, the blue line. Which of these two models does a better job of describing how the shoe length and height are related? So again, would it be the black line, 130 minus 5x, or the blue line, 25.3 plus 3.66x. Well, thinking about the data and what we answered before, we said that it was a positive relationship. So of these two lines, the only one that shows a positive relationship is the one in blue, y equals 25.3 plus 366x. That would be the better fit for our data based on saying there was a positive correlation. Again, it's going in the direction of the data points. It's splitting it about evenly above and below. So it's meeting kind of 2 out of the 3 requirements for your best fit line. So if we're going to use this model, what predictions can we make? And when we do make the predictions, how accurate are they? So one way to find the line of best fit between two variables is to use the proposed line to predict the y values for the points in the scatter plot. These predicted values could then be compared to the actual ones. So if we have y equals 25.3 plus 3.66x, can we use that to predict the man's height if the shoe length is 12.6 inches? Well, if we know the shoe length, that's our input, that's x. We could substitute it into the equation and find the predicted height of the individual. So let's do that. If I substitute in my 12.6, and I follow my order of operations, doing my multiplication and then addition, we would end up with 71.416 inches. So again, that's on the fit equation that we were given. How accurate is it? Well, if we look at our data table, we could see the man's actual height was 74 inches. So we can calculate the error in our prediction by subtracting the predicted value from the actual value. This is what we call a residual, the prediction error. So if we were going to calculate the residual for this data point, we would take 74 minus 71.42, and that is our prediction error, the residual. So our residual here is 2.58. Again, if it's a good line of fit, the residuals should be very minimal to show that your estimated is very close to the actual value. So again, just how accurate is our model equation for our line of fit? In order to do that, we're going to calculate the residuals and see what ends up as our sum. So the first thing is we're going to find the values for the predictions based on our equations. So for the shoe length of 11.8, what's our predicted value? 12.2, what's our predicted value? And fill in our table. So I'm taking those shoe lengths, substituting them into the equation for x to see what comes out. And so I got 68.49 for the 11.8, 69.95 for the 12.2. So we have all the predicted values now based on our equation. To calculate the residual, again, we take the actual height value and subtract the predicted height value. So 74 minus 71.42, we got 2.58. 65 minus 68.49, we got a negative 3.49. So could you fill in the other missing residual values based on your givens? By taking the differences, we should have residual values of 1.05 and 0.98. And again, as you look at your column of residual values, the closer they are to each other, the more accurate your equation is. Well, what is our sum of the error? So if we add all of our residual values, our sum is negative 0.60, showing that in total, we were below 0.60 of the actual height value. Now, we also can calculate the residual squared. So we're just going to take these values and multiply them by ourselves and check that sum. So if we do that, our missing values here would be 1.10 and 0.96. And again, we're going to look at the sum of all the residuals squared, which is 34.54. Again, the lower the sum, the closer our predicted values are to our actual values. So when comparing equations for lines of fit, if we have the one that we were using here and we compare it to the other one that we were given, we can compare the sums and see the residual sums for ours. It's much closer together than what the other equation would have been. And the same thing for the residual squared sums. Again, much closer, much lower than what that would have been. So looking at these residual values and residual squareds, and as well as their sums, it tells us how accurate our equation would be. So we made a good choice going with 25.3 plus 3.66x. So let's go over a couple of things. Why do you think some residuals are positive and some are negative? Well, when we calculate the residuals, it was the actual minus the predicted. So depending on our model, depending how accurate it was, that's why some were positive and some were negative. Some were over-predicted and some were under-predicted. So the positives occurred when the actual value was greater than the predicted, and the negatives occurred when the actual value was less than the predicted. The sum of the residuals, so the sum of the residuals we saw is a measure of how good of a job the function does. How close is the predicted values to the actual ones? So remember, the simplest kind of regression line is our slope-intercept, y equals mx plus b. And so when we have that, we want to make sure the residuals are low to reflect the best fit for our data. Why did you get a number close to 0 for the sum? And does that mean all the residuals were close to 0? Well, the 0 for the sum, that means we did a good job writing the equation for the regression line, so the line of fit. And it also means that the majority of the residuals were close to 0. So we were on target to our objective, find the line that would give us predicted values close to the actual ones. And what's the point of the residual squared instead of just the sum without squaring? Well, the reason we use residual squares is because the smaller the sum of squares, the better your model fits your data. And also, we know if it's greater, it's a poorer fit. We like having values of zeros because that means it's a perfect fit for our data. Now we know we're not always going to get perfect fits, but we want to get it as close to 0 as possible. When we take the residual squares, it also avoids sign errors, right? Positives and negatives, because a positive times a positive is a positive, a negative times a negative is a negative. So if we take the residual and square it, that helps us with the sum. We're just not missing adding it together. So it's just kind of an arithmetic check for the residual squares versus just the residual. So again, the line that has a smaller sum of the squared residuals for our data set than any other line is called your least squares line, or your line of best fit. It's also referred to as a line of regression. So for our shoe length and height data for the sample of 10 men, the line y equals 25.3 plus 3.66 is the least squares line, the best fit line. No other line that we had would have a smaller sum of the residuals based on the data set than this one. Now we were given two options with our data set. So we want to enter this into our calculator now and find the equation of the least squares line, and to see if what we did with our given two options really is the best fit. So based on our data, again, we have to remember the slope and the y-intercept for our equation was rounded to the nearest hundredth. So we're going to do the same thing for what we come up with in the calculator to make that determination. So I'm going to show you how to do this on a TI-84 graphing calculator. The process is the same, similar for the TI-84 Plus, TI-84 Plus CE, TI-82, TI-83. TI follows the same steps. If you're using Desmos, I will attach another link for you to walk through the process about how you can enter the data into Desmos and come up with your line of fit. So for us, what we're going to do is go to our graphing calculators and enter the data into the lists. So based on what we saw, we did get the equation to match. So once you've found the equation of the least squares line, the values of the slope and y-intercept of the line often reveal something interesting about the relationship you're modeling. The slope of the least squares line is the change in the predicted value of the y variable associated with an increase of one of the value in the x variable. So, given interpretation of the slope of the least squares line, y equals 25.3 plus 3.66x for predicting the height from shoe size for adult men. To remember, slope is the change in y over the change in x. Our y values is talking about the height in inches, and the x is the shoe length in inches. So what does this mean for us? 3.66 over 1 is our slope. So we know graphically that's 3.66 up and 1 to the right. Meaning in the contextual situation means the height, 3.66 inches, always increased for every inch in shoe length. So again, a man's height increases 3.66 inches for every inch of his shoe length. The y-intercept of the predicted line, or predicted value of y when x equals 0. When using a line as a model for the relationship between two numerical variables, it often does not make sense to interpret the y-intercept because an x value of 0 may not make sense. So for ours, explain why it does not make sense to interpret the y-intercept of 25.3 as the predicted height for an adult male whose shoe size is 0. So again, the y-intercept is the starting point with an input of 0. So it's saying that a man whose shoe size length is 0 would be 25.3 inches tall. Well, we know that you have a shoe size if you are existing, right? So technically, if a man doesn't have a shoe length, he doesn't exist. That's why it's not making sense. So this is why we're ignoring it based on our model for the prediction. So we always have to look to see, well, what does the y value or y-intercept tell us about the situation, and does it make sense? It may not make sense to use it, and we have to describe why. If it does, we can describe why as well. So now it's going to be your turn to practice. Given a set of data, can you talk about the correlation between your inputs and outputs? Can you come up with your line of best fit, whether you are using your graphing calculator or Desmos, and then doing some predictions and explanations based on the equations that you get?